And it's okay, you didn't have to get pretty answers, you know, if you got stage 1 correct, that was great. And I know it's
Can't
usually.
figure it out, everybody. I figured it out.
You figured it out? I'm gonna show everybody, because I don't know that it's obvious to everyone for sure. So first off, one thing that I want to point out in question 1 with the line, no one did it like I did, and that's cool. Lots of people did it a way that worked. But one thing you should be aware of is this thing called point slope form. It'll come in handy many times of a line, and that is you're given the slope and you're given a point. It can be any point. Here we have 2 points, so you could use either one, but I'm going to call it x sub 0, y sub 0. Then the equation of the line is constructed like so, which is a little bit different than what I wrote on the solution set. But this is a really good thing to know, to have ready. A very common way to do this was to like find the slope. So you got your slope, which was 1, and then you put that in here, and then plug in any one of the 2 points and find the y-intercept. That works too. This has its own advantages though, for sure. As long as you get it done, that's all that matters. Get it done right. And then number 2, I wanted to explain how I got my final answer. So quite a few of us got to that. And there's actually one thing I want to say about this app before, I'll go back, but this guy here, the natural log of 1 over something is the negative of the natural log of that something. So if you have a reciprocal in here, you can make it unflipped and put a negative out front. So that was the first thing I did here. So if I make that natural log of 4 over 1, which is 4, then the negative comes out front and cancels that negative, so I get that. And then this is just 1 over 1/5. And that's 5. So that was kind of my process on those guys there. But this is cool. This is great. It works. Plug it in your calculator, get the same answer as I get. Does that look okay, Addie? Sorry, your furrowed brow. Yeah, you're okay? All right. One thing to keep in mind is that if you have an exponential equation like this, this is exactly the same thing. You can rewrite that as this equals this. This is one of those things that, you know, just like the sine and cosine graphs, I'd have nearby, because it's going to let you do all sorts of useful things from time to time. So when I have an equation that says something like this, e to the negative 0.2t equals, what was it, a quarter? Probably, yeah, a quarter or something like that. Yeah, I guess that was eventually what you got. So look what's in the box, the negative 0.2t, and then here's the 1/4. And I can easily just translate that down to here. And now the t isn't inside, it isn't trapped inside there. So this guy can help me rewrite this immediately like this. And however you understand that works, as long as you understand it. Asha, do you have a question for him? Okay, no, it's all good. You keep doing what you're doing. That's good, just checking. Is there anything you're confused about on there? If you think like I graded something wrong, just stop by after class, we'll fix it up. Happy to make sure you get what's coming to you. We all good? Cool. We'll do another one of those probably next week for sure. And you'll get a chance to ace this next one. So like on the exams, like the way exams will work is I will give them back to you and you'll have a chance to do corrections. But like on this quiz, take this quiz as an indicator. If it didn't go well, you probably need to adjust what you're doing, right? It's just like an indicator, like, am I studying right for calculus? And if this didn't go well, talk to me and we'll figure it out. We'll figure out what you need to do different. And I'll probably drop your lowest one here. All right, so let's wrap up a few things and move forward. If you don't have anything y'all want to talk about. The web work, we got a web work. I think it's due, when is it due, Wednesday? I don't even know when it's due. Some people are already done with it, right?
Yeah, that was my question. When is it?
Yeah, I don't know, I'd have to look at it. Are you done with it?
No, I'm just asking. I haven't
Oh,
started yet.
I feel like, oh, okay. I think like Wednesday.
Wednesday, okay.
Yeah, and if not, just let me know. I'll give you some more. Just let me know, Sam.
I'm reading it.
Okay, I know you. Oh, I know you
I
are.
just wanted to ask.
Yeah, honestly, I just forget what I set
Yeah.
the due date as, but it's probably Wednesday or Thursday. Might be. If you go in there and check and it freaks you out, just shoot me an email and I'll tack a day on or so.
Let's do this.
All right.
Just figure it out right now.
Yeah, let's do it right now. Let's check it out. All right, so I want to talk today just a little bit about a mathematical concept called continuity. And it's kind of one of the main applications of the limit stuff that we've been going through. So I've got a function, y is f of x. Let me know when you find that too, Sam,
Yeah,
please.
I got it.
What was the due date?
16th.
Which is,
Next, not this Tuesday, but the next Tuesday.
oh shit, well that's pretty, okay, I kind of meant this Tuesday probably, but I guess you got till next Tuesday.
Okay, well, maybe then.
Maybe don't wait till
I
then.
won't, that's for sure.
Okay, cool. All right, you got a hell of a lot of time to get that thing done. Shit, I probably meant yes tomorrow, but screwed up the date. So continuous means no break. We think about this in terms of the graph of a function. It's easiest to think about it this way. Graph of y equals f of x has no breaks in it. That's the intuitive. This is the intuitive understanding of continuity, that this is continuous because I can ride along that curve and never encounter a hole or an asymptote, whereas this guy right here is broken. So that's not continuous. Let's just maybe get some intuitive ideas before we see the mathematical definition of this. So this is what's called a discontinuity. Here's another one. I'm going to give you multiple examples here. Another one would be, oh, I just have a big hole in the middle. It doesn't have this gap. It's a little less insane, but still right here, I have a discontinuity. I can't touch that point right there. And then I might have something like this. I might have that point defined, but it doesn't fill in that hole. So this is another example of a discontinuity. Let's go through and put a little word by each of these. So here we have a step in the graph. Here we have a hole in the graph. And in particular, the function doesn't even look like it's not defined there, so function not defined at a point. If it was defined, it would have a dot above it, like that guy. So here the function's defined. Function defined everywhere, but there's an unfilled hole. And these are really the main ways that continuity can get messed up. So how do we get around this? Well, can I ask you a question here? Let's call this C right here. Let's make this point C. C. Does the limit exist here at C? No. Yeah, you're absolutely right. What's your intuitive feel for it?
Is it left and the right one?
Exactly. So we got that, everybody feel good about that? That the limit doesn't exist here at C because as I approach from the left and I approach from the right, I don't get the same output value. So let's make a little note here. So the limit as x approaches C of f of x does not exist right there. I put that DNE, it looks pretty sloppy. Tell the building time. Yeah, okay, cool. Let me know if I need to translate any of my writing, please. So limit does not exist here. Left and right don't go. What about here? Does the limit exist? Limit exists here. The problem is there's a hole in the middle. So here we have the limit as x approaches C of f of x exists, but f of C, the function at C, is not defined. Let's look at this last example. Here, does the limit exist? We got limit exists here, right? Looks at least the way I've drawn it. Limit exists. Function is defined, but the function doesn't fill in the hole here. So here, limit exists. F of C is defined, but, and let's write this in a super mathy way, the limit as x approaches C of f of x does not equal f of C. You can't plug and chug your way to the limit here. So let's write this up and then let's talk about this again, because it's been like a weekend, right? A lot of things can fade in the weekend. This says that as I get close to x equals C, what value do I approach? And here it's this value, right? Whatever that is. So this is near C, this is at C. This is at x equals C, and this is near x equals C. And so this is saying the behavior near it doesn't actually model the behavior at the point. So what we're gonna do is we're gonna say f is continuous at x equals C if there is equality here. And let's write that out and talk about how it actually has all these things in it. If the limit as x goes to C of f of x is the value of the function at that point. I'm gonna write that up and then let's talk about it. Give you a second to, oh, I forgot all about my little microphone. One thing I realized, that microphone picked up all sorts of grody noises from my mouth, like when I was eating, it was and I was like, oh my God, that's in the video. That's nasty. So I gotta figure out something better with that. Okay, so what does this mean? This means three things. And it's each of those three things over there that we don't want to happen. So the first one is that when I say this limit equals some number, that limit exists. Limit as x goes to C of f of x exists. So in other words, no breaks like this, no jumps. Just simply writing that that's equal to some value says that that's the case. 2, it says that f of C is defined because I wrote it. So this says the function is defined at that point. So all holes filled or no holes. F is defined at C. And then the third thing it says is, okay, the limit exists, the function is defined like this, but that dang hole is filled perfectly. That the value of the function right there actually fills in the hole. That's the third thing. So the third thing is that limit of x of C of f of x is actually just f of C. And this is why the plug and chug rule works for limits. This is why we can often just plug in the thing and it's equal to the limit because the function is continuous. So put a little note here. This is why we can often plug and chug on limits, because the function is continuous. So you'll see this word coming up pretty often in this class. We're going to assume that things are nice. They're just nice, they're not broken. I'm not going to ask you to do much with this. If you took like MT454 with me, real analysis, we would get really into that. That's not what this class is about. So let me give you a little sample here. How would we get a question like this? Because you will get a question like this on the upcoming web work, which I'll release on Wednesday. So, example. Where is f of x continuous? I'm going to show a little picture. The picture's going to look like this. I'm going to put an open circle, put a point A there. I'm going to put a dot above it, blue. I'm going to come over. I'm going to put an open circle there and an open circle there, and that's directly below it, right above B. And then it keeps cruising. And then we're going to, actually that'll be, I think we'll get it. So the graph looks like that. And I'm asking you, where is it continuous? And I want to show you the easiest way to answer this. Because this question's a little harder than the one that you should answer first. So step one is, where is f not continuous? Because it's continuous in like a billion and infinitely many places. It's really only screwed up in two. So let's list those. So the first problem is at x equals a, and at x equals b is the second problem. That's where it's blown. And so now I want to test your understanding of something else here. Let's see how we're doing on this. Use interval notation to show where f is continuous. Now, what do I mean by that? And maybe we'll just go through this so that when you see it, you've seen it at least once before. And I know you've done this back in the day. What's the furthest left thing that I can't really get to, but what's the leftist? Negative infinity. We always pretend that's the leftmost thing. Yeah? So we're going to start at negative infinity. And I always put an open bracket. You can't get to infinity or negative infinity. So open parenthesis, comma. Now, where am I going to go to? So I keep cruising. I start at negative infinity, keep going. First thing I want to stop at is A. Can't get to A. So I'm going to put A. I'm going to put an open parenthesis because I don't want to include A. So don't include A. Oh, that's the open parenthesis. What is this symbol here? Union. That is the union symbol. So you can think of that as skip, right? It looks like a jump rope, and that's kind of goofy, but it does look like a jump rope. So it helps me to skip over things. So this is the union symbol, and it means or, but it's a great way to skip over things and pick up on the other side. Now I want to pick right up, right on the other side of A. I'm just trying to remove A from the number line. So I go from A up to B, don't include B, skip over the B, go from B to where? Positive infinity. So this notation here is something that you definitely need to be able to use. Everybody feel comfy with that? You've seen it before at some point. Cool. That's enough continuity stuff. I want to do some fun stuff. I mean, this is kind of fun, but it's like there's nothing to do. You guys want to do. I know you need to get some calculus going. So let's get that rolling. Oh my God. Do you know what the Heimlich maneuver is? Oh God. I had to do the Heimlich maneuver on a rabbit this weekend. Yeah. So last year, there was a professor here who was arrested for something terrible. You can look it up. I don't want to get into it. But he was a friend of mine, and I knew he had a rabbit. And so we went and got his rabbit so the rabbit would be okay. We don't want a rabbit. We didn't want a freaking rabbit. We have 2 pugs. They don't want a rabbit either. So we got a rabbit anyway, lives in our basement, owns the whole freaking basement. So my wife was feeding him a grape, and he aspirated the grape. So the little rabbit was like, and she's like, "On, come down here." I'm like, what the fuck? Oh my God. It's like, is he dying? Because he's like 12 years old. That is an ancient rabbit. I don't know if you know much about rabbits. That's a freaking old rabbit. And if he passes in the night gently, we're not going to be upset about it because we love him, but we didn't want a rabbit. But we'll take care of him. So my wife's like, I think he's choking. We look up YouTube videos. How do you do the Heimlich on a rabbit? So you take the little rabbit. Here's the rabbit. You take the little rabbit, you lay them over your arm. His little head's here. His legs flopped over my arm. Take the other hand and hold his head. And do that. So that his internal organs all shove up against his lungs. And he coughed it. He ended up living. I saved a freaking rabbit from a grape joke. Thank you, sir. Thank you. It felt pretty miraculous. But I was like, God, I hope he's choking because I don't want his last moments on earth to be that, the terror of having me do that shit to him. Anyway. So that's the end of that story. Just came up. I need to find my weekend. What's that?
It's an eventful weekend.
It's an eventful weekend. That's why I did very little except grade your quizzes. That was actually nice. That was awesome. That was super refreshing. All right. Moving forward. Let's just recall briefly what happened the last couple of weeks. Remember we had this average velocity of some function. I'm going to get a little fancier with that. So from some time x to some time x plus h. Notice I made it an x, not a t anymore. So that means if I have my distance function versus time, and it looks like this, at some point x, I figure out what the distance, the position is at some time x plus h. I figure that out, so let's get all these guys labeled. This is kind of a picture you should be able to reproduce given enough time. And then we looked at the change in height, so d at x plus h minus d at the start, and then over this distance here, which is x plus h minus x, or just h. So over h. And that was the slope of the secant line through those 2 points. If you like making pictures, this is a fun picture to make. Then we started thinking at the very end of Friday, we started thinking about what happens as these 2 points get closer and closer together, as they coalesce. So what happens as h goes to 0? And what happens is that these 2 points coalesce and that secant line becomes a tangent line. So as h goes to 0, I'm going to draw a new picture over here. We're just at h, or at x now. We've got x and d of x, and this graph, let's see, let me try to make it relatively the same. So I'm right here, and as these 2 points come together, what that turns into is the tangent line, my green. Like so. And this, so let's talk about this. This is what today is all about. So the secant line becomes a tangent line. And this is going to be one of your nearest and dearest friends this whole semester, the idea of a tangent line. It touches the curve in exactly one spot. But it doesn't cross it necessarily. It could possibly cross it, but it doesn't in this particular instance. This also represents the instantaneous velocity. So if I write limit as h goes to 0 of that critter up there, that is equal to the limit as h goes to 0 of that crazy quotient over h. And that, my friends, if this limit exists, so if limit exists, equals the instantaneous velocity. And this is literally what Calc 1 is all about. The instantaneous velocity at time x. It looks like I'm making a fraction there, I'm not. At time x. It is also, and I want to introduce some notation, it is also known as the derivative of d evaluated at x. This is what we're going to talk about today. We're really going to get into the derivative. So what I want you to think about is this. There's this little circle of things that are the same, and if you keep this in your mind, it's going to make calc so much easier, and it's actually going to help you kick ass on that CCI thing you're going to do at the end of the semester, that you know, the thing with all the questions that were impossible to answer. This will help you. So derivative is the same thing as tangent slope, is the same thing as instantaneous rate of change. Is the same thing as derivative. All those, same thing. Keep that in your mind. It's going to make life really good. See if you can get instantaneous. Sorry, my handwriting. I'm getting excited. The more excited I get, the worse it gets. So always let me know. All right. So let me just take a look at my notes and see what I thought we should do next. Yeah. Oh, cool. So Leo, I thought somebody was showing up. We had a person who was supposed to be here. She had some sort of issues, like was not even in the country the first couple weeks of class. Just, you know, how stressful would that be? But I don't think she's joining us, alas. So I actually thought she might be showing up there. Okay, so let's get a nice general definition of the word derivative, and then let's play. And I am going to want you to crank out a few of these by hand. If you had calc already, which many of you had, you learned all these rules, like the power rule for differentiation. I don't know if that rings a bell. Yeah, you'll get to use all those, but we aren't going to like suffer a little bit. We're just going to suffer math-wise, which is the best suffering. Your mileage may vary on that. So let's just get this nice definition out here. that will basically create the rest of the semester for us. So f of x is a function, and x equals a is in the domain of f, which means f is defined at that point. So f is defined at x equals a. That's just fancy math way of saying you can use that value in the function. The derivative of f with respect to, so that WRT is with respect to x at x equals a, is, I'm going to show you some notation. This is notation for what this, all that stuff up there, this is the notation for it, notation. And you read that as, if you're not used to it, f prime of a. That's how I would read that. F prime of a. And that means derivative of f with respect to x at x equals a. This is a lot fancy, easier to say, right? We got that. And it's defined to be the limit as h goes to 0 of, take the point where the derivative's at, move over an arbitrary h, subtract off the value of the function at that point, and divide by h. And put this picture right next to it. Try to shake it up a little bit. If this is y equals f of x, this is x, here's a, here's a little bit to the right, so there's a plus h. Literally, I do want you to be able to make this picture. I think this might actually be on the quiz next week. I'm gonna want you to be able to show me this picture, explaining where this derivative comes from. So here's f at a plus h, here's f at a. And what we're doing is we're taking the limit as these two go together. This ratio right here is the change in height. So that's delta f, which is f of a plus h minus f of a, over delta x, the input. So this is just h. Put a little right triangle there. And as those two smush together, the secant line becomes the tangent line. All right, now we're going to have fun. So let's find f prime of 2 if f of x is x minus x squared. Let's do this one together. We'll do some practice ones. If you're one of the folks who needs harder stuff in here because you're kind of like, oh, I had calc and this stuff's too easy, let me know. I'm making a list of stuff to keep you all busy. I don't want anyone in here being bored or thinking this class is easy. We can't have that. No, I'll help you out. Just let me know. So let's write out the definition, which you should be able to do. That will also be on the quiz. Limit as h goes to 0 of f of 2 plus h minus f at 2 over h. Hey, could you work on that for a sec, please? Let's crank that sucker out. So step 1 is to simplify after this. Take the 2 plus h, plug it in here. And let's see how that's all going. I'll come around and help. What you up to there? Yeah, I thought you were doing something creepy with, not creepy
No.
with your phone. No,
Yeah.
something with your phone. I thought you were
No,
texting.
yeah.
You had the look of a texter.
No.
Well, yeah, this is almost, but that actually would be 2x if we were doing the
Right,
calculus.
yeah, right.
But
right,
what I
right.
want you to do,
Yeah.
my friend Leo, is that. The
Okay.
painful way. No, we're suffering today. We're gonna carry the rocks from one end of the yard to the other and then bring them back one at a time. This is how we get strong. We're gonna get strong, right?
Yeah.
Do you know what to do? Are you feeling like you're not sure what to do?
No, I got it.
You got it?
Yeah,
Oh,
yeah,
okay.
Yeah, I got it. Yeah.
It's going well. Let me check on it. I think you said done. You don't know what to. Okay, cool. So, this function here. Let me show you how to think of this function. So f of whatever's inside there is whatever's inside there minus same thing squared. That's how to read this. This is a rule for whatever's inside here. Do this with it. Okay. So see, now I've got 2 plus h in there. So f of 2 plus h is equal to 2 plus h. And then what? Yes, ma'am. Squared. So the next step is to replace this with this. And then this is just put 2 in and subtract that off. And then divide it all by h.
So 2 minus 2 squared.
Yeah, yes, yeah, exactly. Yes, let's put that here. So the minus 2 minus, yeah, just yes, ma'am. Perfect. And then we're gonna have that all over h. Sorry, that's not quite. But this expression here goes to that. Do you see?
Yeah.
And then I'm gonna FOIL that guy. Gonna do all the, distribute the negatives and simplify now.
Okay.
Sound good?
Yeah.
Okay, cool. How you doing, Eddie? Things going good? I think so too. Yeah. Joshua, you good, my friend? Okay. How's it going? This is such a pretty, did you make those by hand or is that like, did you use like a stick?
It
Damn.
like goes to like normal.
It's freaking amazing.
Yeah, like the app, like, so.
Okay.
every circle would-
Cause that's what mine would look like. Awesome. But you're good on this?
Yeah.
Doing good, Sam? Yeah. Yeah. Well, let's see, so. Okay, that all looks good. No, you're doing great. Just, I would FOIL that sucker out.
Yeah, I was what I would do.
Yeah, that, things will get better then.
Okay.
What we doing here, Sophia?
Is that how you do factors?
No.
So,
Yeah.
how would I?
Can, yeah. So, this function here, here's that one. It's all good, it's all good. So this really means f of whatever's inside here equals, take it. So it's a rule for converting it. So if I have 2 plus h in there,
Oh.
you see, 2 plus h minus quantity 2 plus h squared.
Okay.
Does that make sense? Okay, there you go. That's why we do what we do around here. I'll start cranking on it as well. We're gonna do quite a few of these today. Use lots of parentheses to keep yourself safe. It's better to err on too many parentheses than not enough. So especially when you subtract off f of 2, just be careful with that. slow down just to make sure we can check ourselves. You can always do a sanity check on this. When you get to this stage, all the constant stuff should cancel out. You should have only terms that depend on h in the top if everything has gone well. And I see that I've got 2 plus 2 minus 4, so they all cancel. That tells me it's kind of a first sanity check, that you only have h things in the top after you do this and simplify. And what do we got? We got minus 3h minus h squared over h. I can imagine all sorts of weird things happening from this point. Not you, it's everybody. I kind of want to stop here and just see how we're feeling about this so far. Reluctant thumbs up, yeah, kind of like, yeah, but if I felt like really looking at it, I would probably give a thumbs up. Asha, how are you feeling about this? Yeah, do you want me to go through it?
No, it's good.
You're good? Okay. Leo, you good?
I'm great, yeah.
Okay, cool. All right, so I know that things are kind of going well because the 4 and the 4 canceled with each other, and there's just h stuff in top. Now, here's a spot where things can get weird, and I want you to proceed carefully because I'm gonna factor. You can't cancel from a sum. If you have a plus b over a, don't do that shit. That don't work. That's not legit. A times b over a, definitely. So before you cancel, and I'm sorry, I see spit coming out. I'll be careful. Sophia, spit at your feet. So can factor this sucker out first. So this is, I'm gonna pull an h out, and I'm left with minus 3 minus h over h. So notice that when I go back, it's minus 3h minus h squared. That's the same thing. Now I can cancel. And when you get to this point, look, how does plug and chug work? What happens when I try to do plug and chug? Right here. If I try to plug in 0, what do I get? 0 over 0. So notice that, and this will always happen at this stage. You'll always have that 0 over 0 if you try to evaluate. So you gotta cancel. That's what we talked about last week. So this is lim, as h goes to 0, minus 3 minus h. Now plug, because this thing's continuous at 0, so it's no big deal, and I get equals minus 3. Did everybody else get minus 3? Okay, cool. Addie, you got a minus 3 too?
Yes.
You all good? Okay. All right. Let's take this a little bit further. That's a kind of, what if I asked now, what if I said, oh gosh, could you, I actually meant, could you do this? And you're like, God damn it, dude. We just did that. Could you not have remembered before we did that? Well, we have a better plan. What we're gonna do is come up with a general formula. So I'm gonna work through this one. Let's find a formula for f prime of x where this can be any value. And then we got a formula, and we don't have to go through and do this every freaking time. What we're gonna come up with is a formula, and these formulas are all part of the calculus of derivatives. And the derivatives, the calculus just means method. It's just a fancy word for method. It's the method of derivatives. That's Calc 1. And we're about to come up with our first lovely rule here. So I'm going to say that f prime of x is the limit. I'm doing the same thing as I did over there. It's just instead of a 2, I've got an x. So the limit as h goes to 0, f of x plus h minus f of x over h. Know this definition. definitely on the quiz. What is the definition of f prime of x? And I want you to be able to spit that out. How do you study something like this? How do you get ready for a quiz that has this on it? Let's talk strategy. Sam, what do you do to like prepare for something like this?
Well, I look over multiple times.
Multiple times?
And I look back through all the examples and see what, like in that example, how it's 2 plus h and f of 2.
Yeah.
It's the exact same thing, just in terms of x.
So to memorize this formula, would you just write it a bunch, or would you got a different method?
I would read it, then put my notebook off to the side, walk around the room and try and say it out loud. If I can't say it out loud, then look back at it again. If I can, then I'm good.
There we go. That's how we do it, right? So you're gonna write this down, you're gonna cover it up, you're gonna write, and then you're gonna, you might do weird stuff. Who knows what, I hope you don't write like that. Just weird shit like that, and you're gonna go, oh, that's not right. Yeah, look at Addie, it's making Addie upset. I gotta take it off here. So you're gonna just practice writing that until it's perfect. And then you got it. That's easy, right? That's low-hanging fruit. You can control this. So this is lim as h goes to 0. Now I've got my function. So f of x is x minus x squared. So f of x plus h is x plus h minus x plus h squared. I'm just gonna put that here. And then f of x is just the function. So I'm gonna put here brackets, x minus x squared. Sorry, it's getting kind of crowded over there. Keep that kind of off to the side. So this is f of x plus h, and this is just f of x. And then I have that divided by h, and it's the same game, right? Now I just gotta do the algebra, see what happens, so let's do that. X plus h, gotta FOIL this sucker out. I'm gonna put in parentheses. I FOILed that, right? X plus h times x plus h. Get this guy. And then here I'm gonna distribute minus x plus x squared all over h. If I've done this well, all the x stuff, that's pure x stuff in the top will cancel. And I'll just have h things in the top. So I gotta check this out. Let's see if that happened. So here's a positive x, here's a negative x. Here is a negative x squared and a positive x squared, so that cancels. And then I'm left with stuff that only uses h. So we've got h minus 2xh minus h squared. I'm distributing the minus over h. Almost done. If you try a plug and chug, you get 0 over 0. So you know you need to factor. So you can pull an h out of the top. Notice how I did that. Then I can cancel. There's the problem. That was the 0 over 0. Now I eliminated it. Notice how I'm also carrying along. This is something that I want to see you do. Carry that limit along until you've done it. So carry the lim until you take it. Because it helps to remind you. You're just using this to help keep your brain straight. What has to happen still? Haven't done that. And then here we just got this guy. Now I can plug h equals 0 in. And I got it. All right. Yeah, look okay? Yeah, nice. Now we got a freaking formula that I can use anytime I want. So if I said to you, hey, what's the tangent slope at 3? You just go, oh, it's 1 minus 2 times 3. That's 1 minus 6, negative 5. Can I ask you another question? Where's the tangent slope equal to 0?
-1/2.
Not negative 1/2.
1/2.
1/2, positive 1/2, yeah. So the question I was asking is, where is f prime of x equal to 0? I.e., where is the tangent slope 0, horizontal slope? You get m equals 0. So I'm going to set this equal to 0, and I'm going to solve and get x equals a half. We don't even know what the picture looks like, but we know that. So that's kind of cool. We get information directly and inversely about the function itself. Any questions on that? Because I kind of want y'all to try one again. Okay. Let's see, what did I have next here? Well, that one looks that doesn't look fun. Why am I being like that? So forget it. We'll do one together. Because I'm looking at these and I'm like, I don't want to make you do that. I was like, I must have been feeling really evil when I thought of those. Let's do one together. In fact, let's look at an interesting example. This is an important example. Suppose f of x equals the absolute value of x. So the absolute value function, we plot it out. Let's think about this. So the absolute value of x, there's a couple ways you can think about this. First off is, if I have the absolute value of a positive number, it's just that number. So if it's like 7, it's 7 comes out. So it spits out the thing inside here if it's positive or 0, right? So absolute value of 0 is 0. Absolute value of 3 is 3. Just spit the dang number out. What if the thing inside is negative? What's the absolute value of negative 3?
3.
3. How do you move from negative 3 to 3? What did you do to it?
Ignore the sign.
Ignore the sign or take the negative of it, right? So here I spit out the opposite of x if x is negative. This is a very interesting definition. It's kind of weird. Have y'all seen this before at some point? It's not something you always see. So that tells me how I can graph this. This is a piecewise function. So notice it's y equals x over here, so it's just good old diagonal. But when x is negative, it's y equals negative x. So it looks like this. And x is less than 0. So you get this sharp point. That's the key thing here. We get a sharp point. I want to make that noted. Sharp at x equals 0. So I want to think about, is this function, what is its derivative at 0? What happens when we try to find that? So what is f prime of 0? Let's look at it. Let's use the definition. So f prime of 0 is the limit as h goes to 0, f of x plus h minus f of x over h. This is the thing you'll just remember. Oh, sorry, and this, I know this is 0, so it doesn't have an x in there anymore because I'm doing it just at a point. All right, so this is equal to lem, h goes to 0. This is just f of h. So it's the absolute value of h minus absolute value of 0, which is 0, cool, over h. And let's simplify one last time. Okay, let's look at that. That's weird. The absolute value of the h over the h. So if we can figure out what that limit is, we've got the derivative. Well, we know how to work with this thing. We're gonna actually do left and right hand limits on this. Because the definition changes if the input is positive or negative. So we're gonna do piecewise, or not piecewise, but each side. Let's do each side separately. So first off, limit as h goes to 0 from the right. This is what I mean by from the sides. We've got absolute value of h over h. So notice that when I come in from the right, h is positive. Right? H is positive on the right. So I'm going to just use that top definition. So since h is positive, absolute value of h is just h. It's a positive number, just spit it back. So this is limit as h goes to 0, h over h. Now I try to plug, I get 0 over 0, that's no good. What could I simplify to? 1. And then when I say it's 1, there's no h's, we're all done. Make sure you see that. And look at this. Remember, this is the tangent slope that we're finding. This thing is its own tangent slope. Over here, the slope is always 1, no matter where you're at. No matter how close you get to 0, the slope is 1. Let's do the other side, though. And let's put a little but, because something weird is going to happen. From the right side, or the left side, we have lim as h goes to 0 from the left. I put a little negative sign. Absolute value of h over h. And this is equal to lim as h goes to 0 from the left. Here h is negative. So like h is negative 1/1000th. To get the absolute value, I have to slap a negative in front of it. I'm using that definition. So absolute value of h, when h is negative h over h. That was already there. What does that simplify to? -1. Limit from the right was 1, limit from the left is -1. What can I say about the limit itself? If the left limit and the right limit aren't the same, what do you say?
Does not exist.
Does not exist. So this limit does not exist. Because, let's summarize just really quickly. Because left hand limit, LHL, equals -1, but right hand limit, RHL, equals 1. They're not the same. I can see that the tangent slope along here is -1. That line is slope -1. So any point on here has this tangent slope that just falls right on the curve itself. And over here we've got m equals -1. So that limit does not exist. This does not exist. So the function is not differentiable at 0. And from here, there's a rule that we'll come up with, like kind of a rule of thumb. You won't have to do this. I'll never make you do this on an exam, so don't stress about it. But I want you aware of it, that absolute value of x is not differentiable. That's a new word. I haven't even talked about the word differentiable. It means that limit doesn't exist at x equals 0. And let's think about that point right there. That is sharp. Anytime your graph has a sharp point in it, it's not differentiable there. So sharp points on the graph mean that we are, I'll put a little double-headed arrow here, are the same as not differentiable at that point. So let's do a little summary here. What if I have a function that looks like this? Let's do this. Something like that. You have some fun with it. Just make a little sharp point at 3 and another sharp point at 6. Like that. So that's supposed to be sharp. These are called cusps. Those little sharpies like that. Cusp point. So here, this function f of x is differentiable. Differentiable everywhere except the sharp points. X equals 3 and x equals 6. So could you do me a favor and just write where it is differentiable? So interval notation, just to practice that, interval notation, f is differentiable on, and give me the, here, I'll get you started, I'll minus infinity. What's that gonna look like? Let's just practice writing where it's good. It should look something like that. As long as, just making sure we understand that notation and how to go from the stuff we're taking out to the stuff we're leaving in. Where's that function continuous? Everywhere, right? Yes, so negative infinity to infinity. This thing doesn't have any breaks in it. Sharp points aren't breaks. So this is continuous everywhere, but it's not differentiable at 2 points. Cool. Let's see. I think I lost my teacup. Do you see it anywhere?
This is one over here.
Yeah, it is. Thanks. Oh, I should have hiding it. Nice. Thank you. If you ever want tea, come by my office. I'm like a tea fanatic. I'm like addicted to tea. I've got so much good tea. Earlier this year, I started getting really into Chinese tea and Taiwanese tea. And you come by, I'll hook you up. Okay, let's just wrap up. What do we got? 5 minutes left. We got one last thing. So let's start thinking about rules of differentiation. And now the fun is really going to start, because once we start taking derivatives, it's a whole different math. The calculus is a different thing unto itself. So even if like factoring and all that stuff is rough for you, I've often found people who have maybe weaker backgrounds can still just kick ass at this stuff because it's new. It's a completely different way to approach math. So, rules for differentiation. First off, let's introduce some notation. If f of x equals x to the nth power, so that is x raised to any power, x cubed could be x to the 1.2, anything like that, then f prime of x is equal to n times x to the n minus 1. We're just going to stop with this for today. That's called the power rule, because we have a power and we're doing stuff with it. So this is the power rule for differentiation. So, let's do some examples. Let's actually show one other bit of notation here. Notation, if I write d dx of f of x, this means find the derivative of f. That word is derivative, my God, of f of x. I.e., it's the same thing as f prime of x. These are the same thing. So this means you got a problem to do, this is the same problem. But you're not gonna go to that limit, you're gonna use a bunch of rules that we put together. So for example, find the derivative of x to the third power. Now look at the rhythm. Bring the exponent out front, decrease the exponent. You gotta do it in that rule. So I'm gonna bring the 3 out in front, and then I'm gonna make the new exponent 2. See, the exponent comes out front, old exponent goes down by 1. Does this look familiar? My calc friends, have you seen this? Yeah, this is good. I have derivative of x to the 5th. It's bring the 5 out in front, x to the 4th, exactly. Now let's have a little bit of fun. How do I do that? Yeah, beautiful. Convert it to a power first. So this you can't do until you convert it to x to the positive 1/2. Now you can rock it. Let's rock it. And then I'm going to challenge you, rewrite it without a negative exponent when you're done. You take the derivative, then rewrite that derivative where there's no negative exponent. I guess Addie's already done this. You probably did it already, didn't you? Like just by default. Oh, it's so nice. You got it? You good? I'm close. Slow down. Is it not? Slow down. Slow down. Rewrite that as x to the 1/2.
Yeah, because then you flip, you flip it in towards bottom,
Yeah.
and then,
So what's wrong with your answer? You're right, but what's wrong with your answer? Why is your answer not the actual derivative? It's close. I wouldn't send a rocket into space using that computation.
no.
At least I wouldn't do it while I was in town. Bring the 1/2 out front. Decrease by 1. You're gonna get real good at subtracting 1 from fractions. Leo, what's wrong with yours? What did you miss?
I was missing that half. Yeah. I
You
forgot
missed
to-
the 2, you lost the 2, right? So take this, and this is a negative exponent, so it's 1/2 times x to the 1/2, or if you want to go all the way to pretty town, you just do that. Can I answer any questions about that? And it's, if you're like, oh shit, I don't know what's going on, you're gonna get lots of practice, don't worry. Tons of practice. Let's do another one. Convert it to a power. And then I'm just gonna give Addie another one right here. These will be the last, yeah, we only got a couple minutes, let's just practice this. Ouch. And there we go. this. Yeah, you are. Yes, you are. Yeah, beautiful. Slow you down at all? Yay! Now I have a new, that's my goal for now. Definitely help. That is x to the negative 1/2. If that is uncertain to you, let me know, we'll make sure to talk about it. But the fact that this is in the denominator says negative exponent, it's square root, so that's a fractional exponent. And then once you get that, you stop thinking and you just do the plan. -1 comes out front. -1 minus 1 is -2, so it drops to -2. Here, the -1/2 comes out front. What's my new exponent? -3/2. So we got -1/2 minus 1. That's -1/2 minus 2/2. That's a good old -3/2. Another thing you're gonna get so freaking good at this semester, doing this fraction stuff. I think, did you have that, Addie?
Yeah.
Yeah, okay, all right. I kind of thought so. So then this one here, I would rewrite like this, but I wouldn't have to, but I could. And I like pretty math symbols, so I like that. Same answer, you know, one's not righter than the other. And then on this one, I would probably do this. And thinking about what that means, if you're kind of like, what is a fractional exponent? It means that you're taking the root of that thing raised to a power. So if I have -3/2, or 3/2 down here, that's actually 2 times the square root of x cubed in the bottom. Little bit of review. All right, dear friends. Good work. Thanks for being here today. Be really weird